Welcome to the lecture on the CAP theorem. So the CAP theorem is a very important theorem in the design of distributed systems and distributed databases. So in this lecture, we will discuss many other aspects related to the C of the CAP theorem, which is consistency. Right. So think of this lecture as a lecture where we discuss issues related with consistency and issues related with the CAP theorem. So the basic idea of the CAP theorem is like this. So this theorem and an extension were initially kind of you know were put forth to the community basically as a conjecture. As a part of a talk, it was put forth as a conjecture, and it's proved much later, in some cases by the same person, in some cases by others. Say the PODC conference, which is one of the top conferences in distributed systems, Eric Brewer made the following conjecture: that you cannot design a protocol or a web service that simultaneously at the same time guarantees the three properties, which are as follows: consistency, availability, and partition tolerance. So we'll discuss what these are, but essentially these are desirable properties of any distributed system or any database where you want the data to be consistent. Consistent with what? Consistent with specifications. What kind of specifications? Well, we will see. Availability means it should be available in the sense every request gets a response. And partition tolerance means even if the network kind of becomes two separate partitions, the system is still operational. So he said you can't guarantee all three together. So this may sound obvious, but it wasn't, or it still isn't, if you actually rigorously apply it. So how do we understand them? So we need to understand that all of these theorems basically came out of the database literature. And in the database literature, we have the classic acid semantics, which is something that needs to be discussed first before we get into the CAP theorem. The operations are atomicity. So the idea is that either a single operation or a bunch of operations known as a transaction, either all of it successfully completes. So this is called a commit event, or it fails in entirety. So it appears as if the entire sequence of operations had never started in the first place. The next is consistency. So as I have discussed, consistency means the result is consistent with the execution. The result of an execution is consistent with specifications. Of course, the specifications may themselves vary, but still there are some commonalities in different specifications which we will discuss. Isolated means it appears as if the transactions which are not committed are isolated from each other. In the sense, it appears that if, let's say, two transactions, like two bunch of database transactions, are happening at the same time, then they are happening in isolation, which means one cannot see the updates made by the other. Final is durable. Durable means once the transaction is committed, so once we are done with an operation, the changes are permanent. So basically, they are written to permanent storage. So distributed system services clearly need a different model. The ACID model will not work for them. So in this case, we adopt a different model, which I will describe next. So let us discuss consistency. So the dictionary meaning, as I said, is that the outcomes of an execution should satisfy some written specifications or some intuitive notion of correctness. That's the dictionary meaning. So if you break it down, so we can break it into several components. The first component would be atomicity, which means that all operations appear to take place instantaneously. So it's as if, given an operation or a bunch of operations, it appears to take place instantaneously in the sense you can't see any intermediate state. So let us first define some terminology and then I'll explain. So let wx1 mean write 1 to the global variable x. Let rx1 mean that I read the value of global variable x to be 1. Let p1 and p2 be processes p1 and p2. And let x and y be global variables initialized to 0. So what we have over here is p1 and p2. two processes, processes in a distributed system. So of course, whether you have shared memory or not, it doesn't matter. But in this case, let's assume we have shared memory. In the sense they are operating on the same object. And the objects are read-write objects and they are of type X and Y, both initialized to 0. So let us look at this execution. You write 1 to X, write 1 to Y. Read 1, read Y equal to 1 and then you read X equal to 1. So this is the execution. So what we want to do now is we want to see why does this example have atomic writes. That is because we can lay the operations out in a sequence where we'll first have this Wx1, then we'll have Wy1 which goes over here. We will read Y to be 1 which again goes here, and we will read X to be 1 which again goes here, right? So Wx1, Wy1, Ry1 and Rx1. So as you can see, we can lay them out. And it appears that the write happened at one instant. Then the next write happened at one instant. Then the read again happened at one instant. So reads in general are atomic in all kinds of systems. Writes may not be. So it read, y. You wrote y one to y. So you're reading one. You're reading y is equal to one. And you wrote one to x. So you're reading x is equal to one. So you can lay them out. Furthermore, the sequence is legal, which means if you look at every read, it fetches the value of the latest write. Again to the same address, it is fetching the value of the latest write. So ry1 is providing you wy1 and rx1 is providing you the value written by wx1. So this is clearly a sequence with atomic events, and this sequence is also legal. What else? So what else is special about this sequence? So let's look at this sequence once again. Let's not look at the title of the slide yet. So we can lay them out in an equivalent order. So of course these are two separate processes, but we can lay them out in a sequential order where it will appear that some master execution engine is choosing one operation from here, then the next, and so on. So you have Wx1, Wy1, Ry1, and Rx1. You note the operations, order of operations within each thread. So what we see here is that within the thread, this is the first instruction, this is the second. So clearly the the intra-thread order is Wx1 first and Ry1 after that, and we get to see that. Similarly, we see Wy1 first and Rx1 after that, so we also get to see that. So what we see is that if we create an equivalent global order, number one, it is atomic because it appears that this entire operation executed at one instant of time. And this is true for the rest. It is legal. As well as the order of operations within each thread is the same as the order in the equivalent global order. So this is also known as the program order. So the order within a thread is also known as the program order. So this particular execution or its outcomes rather are such that, so let's read this. So we can reduce a parallel multiprocess execution. So in this case, we have a parallel multiprocess execution because we have two processes, P1 and P2. We are kind of reducing it to a sequential execution where three things hold. Each operation is atomic, the sequence is legal, and the intra-thread order or the program order is respected. So all three things are happening at the same time. So it appears as if you take the operations of the different processes and the you can interleave them the same way you take your fingers and you can interleave them. You can interleave the operations, so you will have different global orders. But the idea is that the execution is consistent with at least one global order where three things are there: atomicity, legality, and the program order is respected. So any such execution is known as a sequentially consistent execution. You can clearly see where the name comes from. The name comes from the fact that a parallel execution is being equated with a sequential execution. So you say that the execution is sequentially consistent. So SC is by far the most popular consistency algorithm in, I would say, all of distributed systems, even though many a time enforcing SC itself can be quite impractical. But still, the idea is that SC is quite popular. It was published or proposed by Leslie Lamport way back in the 70s. But henceforth, it is kind of regarded as a gold standard of consistency in distributed systems of all kinds. So, can we have a non atomic execution? Well, we can. So, let's see. So, let's assume we have three processes and you write 1 to x. So, process 2 reads x and it sees that the value is 1. So, this is fine. You can see that there has been a data transfer like that. And then assume that you respect program order in the sense you finish this operation and then you do this. So after reading x is equal to 1, you write y and you write the value of 1 to y. Then again you read y to be 1 and finally you read x. So what do you expect? You expect that since there is a causality, right? Since there is a chain of dependence over here, if you had written 1 to x, you'll also read x to be 1. So you would expect to see Rx1 over here, but let's say you don't see it. If you don't see it, what does this mean? This means that this write has gone to P2 first and this write has gone to P3 much later, right? That is what you have seen, that the write has gone to P3 much later, and it has, at this particular point, it has not reached P3, but it has reached P2. So this means that if the program order is respected, we expect P3 to read x equal to 1, but in this case, it hasn't. It has read x equal to 0, which essentially means that the writes are not atomic in the sense that the write wx1 over here has not happened or has not appeared to happen at a single instant of time. Instead, it is appearing that it is like happening at different instants of time to different processes. So in the first case, it is appearing to have occurred before Rx1. In the second case, it is appearing to happen after Rx0, right? So in this case, the writes are not atomic, and in many distributed systems, writes are not atomic, mainly because to make a write atomic, what do you have to do? You have to broadcast the write to everybody and ensure that a process can only read a write when the update has been propagated to the rest of the processes. So this is an atomic write problem, and of course there are algorithms to ensure atomic writes, but a naive implementation would lead to a non-atomic execution. So in other words, in this case, you can see an intermediate state where the write has gone to one process but not gone to another process. So what is the problem with sequential consistency? Well, if we come back to the same example and the equivalent global order, the idea is you only talk about relative orders. In the sense you say that, look, first this operation happened, then this, and then this. Fair enough. So this you are guessing from the outcome, but the point is you are totally ignoring the real time, the absolute time at which these operations happened. So maybe it is possible that in terms of absolute time, operation 1 happened first, operation 2 happened after that, and then operation 3 happened after that, right? So in this case, what would happen? In this case, operation 2 will not read y to be 1, but it will read y to be 0. Then operation 3 happened and then 4, so the rest are fine. So the issue is that if this was the real order of operations happening, and let's say, with each operation, you can have a start time and an end time. So it is very well possible that after operation 1 ended, operation 2 began. After operation 2 ended, operation 3 began, so on and so forth. So in this case, what you will see is that even though this execution is sequentially consistent, it is not really consistent with the wall clock order, because here we are only talking of relative orders. First this operation, then this. It has nothing to do with real time. But the moment you bring in real time, then, and if let's say this was indeed the real time order, where operation 2 stopped, operation 1 stopped, operation 2 began, operation 2 stopped, operation 3 began, so on and so forth. you will see that the outcome will not be this. Instead, the outcome will change and the outcome will become ry0. So if the outcome becomes ry0, then clearly, in this case, sequential consistency would give you a different answer. And adhering to the real time order, you will get a different answer. So whenever we are fine with just the relative order, we will accept any outcome that sequential consistency gives. But the issue is that given the fact that SC is more of a theoretical model because it preserves relative orders and it preserves read-write relationships and atomicity, we call it a theoretical model primarily because it ignores real-time values and constraints, right? So that's the reason we ignore it. So if we put in additional constraints to SC, we come up with another consistency criterion. This consistency criterion is called linearizability. So linearizability is something which is more powerful than SC, and the reason that it has been added is basically because there were issues with SC, right? And the issues were pointed out in the previous slide. So in this case, the two additional caveats that we add are like this, that every operation of course has a start and end time. So atomicity basically says that an operation needs to appear as if it is executing at a single instant of time. But this single instant of time could be any time, in the sense it could be right over here after the operation has ended. So in this case, the results of the execution will not be consistent with the real-time order of operations. So linearizability doesn't allow this. It says that the time at which an operation appears to complete instantaneously, it still has to complete instantaneously, has to be between start and end. That's the first point. So then another thing it says is that assume operation B starts after operation A ends. So this is operation A and this is operation B. Then in the equivalent global sequential order that we create, right? So we created that in the case of SC as well. SC is sequential consistency. B needs to appear after A, right? So that is clear. So why is that the case? Because clearly, these two are not concurrent operations. That's the reason A appears first and B needs to appear after A. Of course, if there are concurrent executions, like if this is the case, then linearizability does not say who needs to appear after whom because there is an overlap. But again, since they appear to execute instantaneously, all threads should see either appearing before B or B appearing before A in the equivalent sequential order. So these are the two extra conditions, extra caveats that are added in the case of linearizability, which SC didn't have. So they make it like more in line with real-time constraints, right? So this is something that SC didn't have. So that is why we had little bit of an odd behavior as we could see over here because we expected RY0. This was the real-time order, but this was the execution results that we got, which is fine from an SC standpoint, but this is not fine from a linearizability standpoint. Whereas if you take a look at this execution is linearizable, but clearly not in SC. No, I'm sorry, stand corrected. This execution is linearizable. It's also in SC, but this execution, the first one, is in SC, but it is not linearizable. So sorry, I stand corrected. So linearizable executions are essentially a subset of SC, right? So basically SC is a superset of linearizable executions. So anything which is linearizable is in SC, but not the other way around, as we saw just over here, that this is in SC, but it is not linearizable. But this is linearizable as well as in SC. Well, why? Because we can create a sequential order like this: WX1, then RY0, then WY1, and then RX1. So as you can see, this order is legal, right? This order respects program order and it is atomic. So atomicity is there. So given the fact that we have discussed atomicity, how atomicity is added, mixed with reliability and program orders to create SC, and how we add real-time ordering to create linearizability, we can now move forward. So let me nonetheless just summarize with a little bit of extra space that I have over here, and I will do that. So the properties we have are atomicity, then we have program order, legality. So these were properties of SC, where basically you have program order, atomicity, and every read needs to return the value of the latest write. If with this we add real-time orders, then what we get is linearizable. Right. So we have discussed all of that for the sake of, for the purpose of discussion of the CAP theorem. We will only use the only consistency guarantee that we will use will actually be atomicity. So that is what we will use. And we will show that that itself is sufficient to almost prove everything. But since we have the opportunity, let us discuss other types of consistency as well. So you can have causal consistency, which means let's say if there is a write and then there is a read, and after that, let's say there is a write, right? So there is a program order relationship between this read and write. So then everybody should see this write happening first and this write happening later. It should never be the case that you do a read after this, so you see the results of this, but you don't see the results of this. That is because two operations are related with a cause effect relationship. It's causal, right? So you wrote and I read what you wrote, so we have a cause effect relationship. I executed, that's the reason you executed. Again, we have a cause effect relationship. So as long as there is some sort of a cause effect or a causal relationship, we will expect them to be seen in the same order by all processes, right? But if you don't have causal relationships, they can be seen in any order. So a wonderful example can be given to illustrate the point. Let us say we are writing x is equal to 1 and then we write x is 2. One thread reads x, so it sees first 1 and then 2. Well, that's fine. So then as far as we are concerned, if atomicity were to hold, then x would be written first with 1 and then with 2. But what if another thread observes Rx2 and Rx1? So clearly in this case, the atomicity of x is not holding, right? So it appears that we are updating x in a different order, right? So both the threads are not agreeing with respect to the order in which x was updated. And as you can see, there is no causal relationship between this write and this write. So causal consistency at in this point basically says you can see them in any order, which the threads are doing. So this is clearly not sequentially consistent. This is clearly not linearizable, but it is causally consistent. So causal consistency is weaker, right? The same way that SC was weaker than linearizability, causal consistency is weaker than sequential consistency. So we can again define this in a different way. Let us say that we are maintaining many replicas of a variable. So we have multiple servers and they are maintaining many replicas of a variable x. You want to read it or write it. So the replicas themselves could be loosely synchronized, but let's say if you read a value from this set of servers, you may get a replica which is stale. In the sense its value is old, it's inaccurate. But in certain conditions, or let's say in this continuous consistency model, it is guaranteed that whatever is the value of x that you get and whatever is the real value of x, right, which you should have gotten in ideal circumstances, the error is bounded. So again, this is not a very generic model. It is true only for some cases where you are dealing with things like clocks or counters and so on. But again, this is a consistency model where you look at the difference in the values and you try to bound that, right? You try to place a bound on that. So we will now discuss a few more kinds of consistency models from the point of view of a client, right? So who is a client? So assume that you are accessing Gmail. So Gmail is the server, my mobile phone is the client, or you are accessing an office network that has lots and lots of documents, and I may be accessing it using my mobile phone or laptop or desktop. So in that case, my mobile phone or laptop is a client. So from the perspective of the client, so up till now we are looking at it from the perspective of the system, but from the perspective of the client, we could have many consistency models. So let me discuss a few. So let us look at monotonic reads. So if a certain value for a variable was read, so in the sense, let's say, you read an email. Subsequent reads by the same process. So same process means the same mobile phone, where it may connect to the same server or a different server, will yield the same value or a more recent result. So which basically means that if let's say I connect to Gmail and I'm able to see an email, half an hour later I connect to Gmail again, but internally Gmail connects me to a different internal server. I should still see that mail. It should not go away. If this doesn't happen, what will happen is that I may see a mail now, and sometime later I may not see the mail, right? And later when we connect to another server, we may find the mails to be missing, right? So then there will be an issue. So this is the monotonic reads, which is purely from the perspective of the client. We are not looking at it from everyone's perspective, as we were doing earlier. We could have monotonic writes, which means write operations made by the same process happen in order. What would that be? So let's say, in on Twitter, you would have seen many of these tweets, 1 by 2, 2 by 2, and so on, which is like the first part of the tweet and second part of the tweet. So this I do from my Twitter client. But what if Twitter shows the second part of the tweet first and the first part of the tweet? Along with being incorrect, it can lead to quite embarrassing situations. This is definitely not what you expect. And that is why this consistency model, from the point of view of a client, is called a monotonic write. So clearly you can see that if atomicity is there, monotonic reads are not a problem, because once you have read, you will always read it. Monotonic writes are not a problem because once you have written, right? So it is appeared to happen at an instant. So the moment the first tweet is done, you can do the second and it'll remain that way. So I can extend this to have two more models, read your writes and writes follow reads. So read your writes is like this, that if a write operation is done on a process by a process on item X, any subsequent read operation by the same process will at least fetch the write that its own write, or something newer, of course. So why am I saying that? Well, the reason I'm saying that is, let's say you compose a mail and you store it in drafts, and later on you read the drafts folder, you're supposed to see the mail. If you don't see the mail, you'll sort of see the mail vanish, which again is something that atomicity will not allow. So at a fundamental level, if atomicity holds, you will never see that. But if let's say you have different email servers and one email server holds the drafts folder and it has not broadcasted the updates to the other, this indeed can happen. Then we have writes follow reads, a write operation that overwrites a variable will overwrite fully or partially the version that was read. Right? So that's correct. So let's say I read something. I read a document or I read a draft email and then I make a change. So what am I reading? The object that I'm reading is a draft and then maybe I make a change on it. I change a sentence. So I'm doing a write. So what will happen is that if I have read something, the write operation will only overwrite the draft that I have read. It's not that the draft is going to change. For example, what I could have done is that for the same draft, I could have saved it twice, a smaller version and a bigger version. So of course, at the end, the bigger version is the more recent one. So that is the one that should stay. So what should happen is that the next time I open my drafts folder, I should not see the smaller version. I should see the bigger one and there I make a change. But what happens if while I am writing, The write goes to the smaller one and not the bigger one. Again, it can happen if I have multiple servers and these versions or these replicas of the draft mail are there in different servers, and that could cause an issue. But in a good distributed system, it should not happen. Of course, if you have atomicity, this will always happen. This condition will always hold. Again, one more thing, you have reactions to tweets where reaction is a write, but that should only happen after the original tweet has been read. So it should not be the case. You read a tweet, you react on it, but then you see that the reaction is there but the original tweet is gone. So that again should not happen. And atomicity would guarantee that this doesn't happen. So what is the crux of our idea? The crux of the idea is like this, that regardless of your consistency, SC, linearizable, causally consistent. We also discussed continuous consistency where we looked at errors. So, but ideally the error should be zero. Then we discussed client-centric models, different client-centric models. So clearly in the first two, atomicity was common. Causally consistent, we didn't see atomicity. That is why we didn't like the results that it gave. Continuous, again, if you have atomicity, you'll not have an error, right? So atomicity is definitely desirable. And client-centric, if you have atomicity, then you'll not have any problem. So that is why in the CAP theorem, they have taken atomicity as the definition of consistency, by and large. So then, after we have discussed the consistency models, we should cap this discussion with a discussion on quorums. So what is a quorum? A quorum, let's say a quorum in a meeting is what? So a quorum is basically the minimum number of people who need to be present in a meeting to make a decision. So we can do the same if you have a bunch of servers. What we can do is that we can have a write quorum of NW servers. So the write quorum is more than a majority. So you will know that at least a majority have the latest update, right? And so basically, number one, that insulates you against failures. And we will link this with a read quorum, where a read quorum is a set of NR servers that choose the most recent value. So to guarantee that the most recent value is read, the only condition that needs to hold is NR plus NW is greater than N, which basically will then ensure that the read quorum and the write quorum have an overlap, and the overlap will provide the latest value of the write. So of course the implicit assumption in the definition of a quorum and these quorum based writes is that when you write you actually broadcast it to the entire quorum, all of them update it. When you read, you actually read from the entire quorum, and every write is associated with a timestamp, where higher the timestamp, the more recent the write is. And the value that is ultimately returned is the latest value or the value with the latest and greatest timestamp. So this does increase the overhead within the server farm because a write now has to be broadcasted or multicasted to the quorum, and a read is also required from everybody from the read quorum such that you can get the value of the latest write. But this is a price to pay if we are using a set of servers for both performance as well as redundancy. And of course, if you have more servers, it will make the data more available, but ensuring consistency becomes difficult. So you can clearly see a consistency and availability trade off over here. So the CAP theorem is all about trade offs. So, but before that, what is the final word on consistency here? It is that sequential consistency or other similar variants and client-centric models, everybody rely on atomicity. So we will also primarily focus on atomicity as the C in consistency. The rest two are easy. So rest we have discussed, that is not a big deal. The first is availability, which is that every request received by a correct node must result in a response, which means requests must terminate. So, right, so request termination is guaranteed in the sense that every request has to result in a response. The second is partition tolerance, where a partition means that all messages sent from one partition to nodes in another partition are lost. And in spite of that, the system needs to work right, as well and as nicely and as correctly as possible. So what's the theorem? The key theorem is we cannot guarantee both availability as well as atomic consistency for a read-write object in an asynchronous setting where messages can be lost. Right, so in any asynchronous setting where messages can be lost, right, or a partition can be created, we cannot guarantee availability and atomic consistency. Okay, why not? So assume that messages are lost and a partition is created. We call one partition G1 and the other G2. So all messages between G1 and G2 are lost. So if a write occurs in G1 and later for the same variable there is a read in G2, clearly a stale value will be returned because you are guaranteeing availability. You don't have the option of sitting on the request. You have to return whatever you have, and what you have will be a stale value because you never got a chance to get the most up-to-date value. So this would clearly violate atomicity because it doesn't appear that the write occurred at an instant, because the write occurred and much later you made a read from G2 and what you got was a stale value. So the issue is that in this case, you cannot guarantee both availability as well as atomic consistency. And the reason being that it's not possible to propagate the write to G2, and that's why a write will not appear to complete in an instant. And given the fact that nodes in G2 are bound to return a value by the availability requirement, they have to return a stale value which is going to break atomicity. So what we can see is ensuring CAP, consistency, availability, and partition tolerance. In this setting where messages can be lost and we have an asynchronous setting is not possible. Let's have a corollary. So we cannot again guarantee both availability and atomic consistency for a read-write object in an asynchronous setting where no messages are lost. So this is much stronger. This says that even if no messages are lost, we still cannot guarantee both of them, right? The argument is the same as the FLP theorem. Given the fact that we have an asynchronous setting, a node doesn't know if a message is lost or the sender is just slow. Right? So this was the key aspect of the FLP result. So if you go back to that, where we argued that in an asynchronous setting, you simply don't know, if the node is still replying or if a message is genuinely lost or the node has developed a fault, the node is dead. It's not possible to find that. Given it's not possible to find it, this situation is no different from the earlier situation where messages are lost because you can't find out anyway whether messages are lost or nothing is lost. Given the fact that it's not possible to find out, this situation is exactly similar to the previous one, right? Insofar as the perspective of the node is concerned, and in the previous one we couldn't guarantee availability and atomic consistency, so we can't guarantee it over here as well. Another argument: assume the earlier case where messages can be lost. No problem. So do one thing: don't lose them. Whichever messages you intend to lose. So we are looking at a master oracle which has control over the network. Just keep them in a cold storage, right? Don't deliver them. Keep them in a cold storage. The nodes will perceive that these messages are lost, but they are actually not. They are in a cold storage. At some point from the proof, right, we will see a non-atomic execution. Right? For some example, we will see a break in atomicity. At that point, release all the messages in the cold storage. So as far as we are concerned at this particular point, when all the messages have been released and also delivered, no messages are lost because the cold storage is empty and every message is accounted for. But we have still seen an non-atomic execution. So no messages are lost, yet the execution has still been seen to be non-atomic. So this means that even if there is no message loss, we can still construct an example where if availability is guaranteed, atomicity has to be compromised. So there is a trade-off between them, or rather both cannot be guaranteed. So which essentially means in an asynchronous setting, regardless of the reliability of the network, right? So whether you are partition tolerant or not, availability and atomic consistency both cannot be guaranteed. Or if you extend this argument in the CAP theorem, all three cannot be guaranteed. Can we guarantee 2 out of 3? Well, we very easily can. Atomic and partition tolerant. Well, have a central node and ensure that all the updates are there with the central node. It maintains up to date state. If you can reach the central node, return a response which is guaranteed to be correct in the sense it will be atomic. If you cannot reach the central node from a partition, well, don't return anything. Given the fact that availability is not required, we are fine, right? So basically, if the option is there of not returning anything, then of course correctness will always be guaranteed because we will never return something which is false, which is wrong. Atomic and available, well, same idea, have a centralized node for a single partition that will solve the problem. You will both be atomic and available. Don't care about the rest of the partitions because we don't have to be partition tolerant. So other unreachable partitions can be ignored. Available and partition tolerant, well, in this case, there is no consistency at all. So for that matter, any value can be provided, any stale value can be provided. Given the fact that atomicity is not being considered here, there is no problem. Now let us look at a different model. So we have been looking at an asynchronous model up till now. Let us look at a partially synchronous model, which we will also discuss in other papers like Stellar and so on, where clocks are loosely synchronized. There is a bounded clock skew. All network messages are either delivered within T message time units or they are lost, right? So the network is also reliable. Clocks are also reliable. So the theorem is we still cannot guarantee CAP, right? So the all three cannot still be guaranteed. The idea is the same. We divide the network into two disjoint partitions, G1 and G2. A read will happen in one component, a write in the other, as we have seen. Given the fact that the write cannot propagate to the other component, right? Let's say from G1 to G2, the write cannot go. We will never be able to provide the up-to-date values. So atomicity will not hold. If atomicity 1 doesn't hold, if the C doesn't hold over here, then CAP cannot be guaranteed, right? So in this case, regardless of whether you are asynchronous or partially synchronous, we still cannot guarantee all three. If, or let's say even if, the clocks are synchronized and the network is reliable to the extent that it tells you within T message time units, either delivers a message or loses it forever. So there's no cold storage here. Or it will be incorrect to say no cold storage, or rather we cannot use the cold storage theoretical trick to prove something in this case. Now let's look at the corollary in terms of the partially synchronous model. Assume that no messages are lost. If no messages are lost, is there a way out? Well, it turns out to be yes. Use a centralized scheme, which is a single central server that maintains the overall state, and it also answers queries and consider a basic read-write object. So a single central server here, multiple client machines, all of them issue read-write requests to the central server and then return the result. So unlike the asynchronous case, here we can detect message losses in the sense if I send a message and expect an acknowledgement and I wait for 2T message plus the processing time to process my original message, I will get to know some things. I'll get to know whether the message was sent and the ACK was received. Otherwise, I can again send the message again. So let's say if all messages are delivered. If all messages are delivered, I will always get the ACK back, right? So let's not consider the case where either the message is lost or the ACK is lost. But let us consider cases where all the messages are delivered. In that case, I'll get the acknowledgement back. There is no message loss. If that is the case and availability is guaranteed, a response will come. right? So in this case, a response will come, and the response that will come will be correct, right? So we will know if there is no message loss, we will definitely expect a response within a finite amount of time. And if we still use the central server based scheme, this is going to work. Otherwise, a best known value, the stale best known stale value could be returned. But again, in this case, if there is no message loss, then this is a different case, because in this case, message loss can be detected. And given the fact that it's a different case, and if we have availability, responses will come, and the responses will also have the correct value. So conclusions and extension. So the CAP theorem limits what can be done in a distributed system. You clearly cannot have C, A, and P all together. So this has been extended in 2010 to the PACELC theorem. So this actually says something more. So it says that, look, if the network is partitioned, a trade-off exists between availability and consistency, and this we have seen. So this we saw in our discussion, that even if a network is partitioned, then of course there is a trade-off. If it is not partitioned, right? So if, let's say that all nodes are reachable without partitions, then there is a trade-off between else. So this E is for else. Then there is a trade-off between latency and consistency. You can always have a system with no consistency that's going to be very fast. For example, if you have a set of servers and instead of all of them maintaining a replica, you could just say that you query some server and return a stale value, then the latency will be very low, right? And the consistency will also be quite weak. But if I make the consistency quite strong, in the sense if I make this linearizable, then of course a lot of messages etc. have to be sent between the servers to ensure that we are genuinely getting the latest value. So in that case, the latency will shoot up, right? So basically, what is required in a distributed system? It could be SC. So in SC, you will get a solid correctness model. We have not discussed eventual consistency, but there's not a bad place to discuss it. So eventual consistency means that writes are ultimately visible, in the sense that if I'm writing to something, I don't care about the order of writes and other aspects, but writes are ultimately visible. So if I have an eventually consistent system where writes are ultimately propagated, my latency could be quite fast. So as you can see, there is a trade-off between L and C, particularly when we don't have partitions. So this is the PACELC theorem, and this also was formally proven, as you can see. So the first paper by Seth and Lynch was the one that proved the the CAP theorem. And the PACELC theorem, the one that you see over here, was proven actually in 2018, and you can take a look at the proof.